Hello and welcome back to Fourier Transform, the video series where we discover Fourier series and related stuff. And in today's part 11, we will prove a formula for the cosine function which we have used in the last video. Indeed, it was a crucial step in the proof for Parseval's identity for a special step function. Therefore, we have to show this formula to complete the whole proof. So it's a technical video which is only important for you if you want to understand the details of this proof. However, as always before we start with the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, by using the link in the description, you can download additional material for all the videos. So for example, you find printable PDF versions and quizzes for the videos. Okay, then let's immediately start by stating the formula we want to prove here. It's about the infinite series where the cosine is involved and 1 over k squared. And by knowing some criteria for series, you can already check that this is a convergent series. However, we want to have more, we want to have the exact value of this series. And it turns out that this limit is exactly x minus pi squared over 4 minus pi squared over 12. And this nice formula holds for every x between 0 and 2 pi. And in fact also for the boundary cases of this interval. And now please recall that this is exactly the formula we used in the last video to prove Parseval's identity. Okay, in order to prove this nice formula, the best way is to first go to two related formulas and show them. The first one here is not so complicated, it's just about summing up cosine functions. So we take the constant 1/2 plus a sum of cosine functions. So k should go from 1 to n, and inside the sum we just take cosine kx. And here it makes sense to introduce the constant 1/2 as well, because then we can easily rewrite that with exponential functions. Indeed, the cosine function is nothing more than 1/2 times the sum of two exponential functions. After all our discussions with the Fourier series, this should not come as a surprise for you. In particular, it should not be a surprise that now we can rewrite the whole thing as a sum from -n to n. So we get 1/2 times the sum of exponential functions. Of course, this is already a nice formula, but what we want is to get rid of the sum symbol altogether. And we will do that by using the geometric sum formula. However, for that, the sum has to start at the index 0. So the idea is that we go from k is equal to 0 to 2n. Then we have the same amount of terms in the sum, but obviously not the same terms. But we can make the equality here if we just multiply by e to the power minus I n x. And then you should see this is exactly the index shift we needed. So now we have the correct sum here, and inside it we find a complex number we can call q. Or more precisely, it should be q to the power k, which simply means this q is given by e to the power ix. And now what you should see here is a geometric sum where we have a nice formula for. However, this formula is only valid if q is not equal to the real number 1. So the formula also holds for complex numbers, but 1 is still excluded. This is easy to see if you know the formula, because we have 1 minus q in the denominator. In fact, this formula is easy to remember. Just take 1 minus q for the denominator, and the same in the numerator, but there q has the power as the end index of the sum plus 1. So in this case we have 2n plus 1. So this is the geometric sum formula as we have discussed it in the real analysis course or the complex analysis course. So in the case you have never seen this formula at all, please check out these old videos. Okay, and now here in the next step we can simply resubstitute q. And maybe we can also multiply e to the power minus I n x to the numerator here. And then we see that we have e to the power minus I n x minus e to the power I n plus 1x. So from the 2n plus 1 we had before, 1n cancels. Moreover, here in the denominator we just have 1 minus e to the power ix. So now we could say this is already a nice formula because the sum has vanished and we get a nice fraction here. However, the left hand side is a real number and therefore the right hand side should also be expressible with real numbers. And this is not hard to get, just expand the fraction by the correct exponential function. And the correct one here is minus 1/2 ix. This makes sense because it brings the denominator here to a sine function. So maybe let's write the whole expression, which is simply a fraction again. So first in the denominator we have e to the power 1/2 ix minus the same with a minus sign. And in the numerator it looks similar, but there the power is I times n plus 1/2 x. Also easy to see because we subtract 1/2 here. And we have the same thing with the minus sign for the first term here. Hence everything worked nicely here, and what we get, as you can see, in the numerator as in the denominator are sine functions. Of course, the only thing missing there would be a factor 1 divided by 2i, but we can just add it as before. Hence expanding the fraction one last time gives us the result with sine functions. So we have the sine of 1/2 x in the denominator and sine of n plus 1/2 x in the numerator. So this is the whole formula for the sum of the cosine functions. However, it does not hold for every x because remember we have the restriction that q is not equal to 1. And indeed we know that the exponential function here is equal to 1 if x is 0, 2 pi, 4 pi and so on. Hence the formula here does not hold for x as a multiple of 2 pi. Therefore we can say the formula holds for every x in R with the exception of these multiples. So we have 2 pi m where m is an integer. Okay, there we have it. This is the nice formula for x in this set, which we want to use for the next important lemma. I call it lemma because we first have to prove that and use it to prove our general result from the beginning. This means before we can prove our important result for the series of the cosine functions, we first have to prove one for a series of sine functions. In fact, it's kind of funny that a very similar formula for the sine functions helps here. It's sine of kx over just k. And it turns out this one is also a convergent series most of the time, and it has the value pi minus x divided by 2. However, this only holds for the open interval 0 to 2 pi, which is not so surprising because for x is equal to 0, we have the 0 series here, which is obviously not convergent to pi over 2. However, all the other x values give us a nice convergent series. And moreover, if we see this here as a sequence of functions, we even have uniform convergence. However, there we definitely have to go to a compact interval. So for example, we could go from epsilon to 2 pi minus epsilon. So you see, we just need some security distance from 0 and 2 pi. And indeed, any epsilon is already enough for that. So I would say this is also a very nice result, and now we can prove it by using the formula from before. The idea is simply to express the sine function as an integral over the cosine function. And then we can simply apply the sum formula for the cosine function from before. So as always, we start with a finite sum, so we go from 1 to n. And now, as I've already mentioned, this can be seen as an antiderivative for the cosine function, which means we can just write the integral from pi to x. And inside we have cosine kt dt. And now since the sine of k pi is always 0, this formula holds for every x. And now since the integral is linear, we can simply pull in this finite sum. Okay, and now you see we can use our formula from above, and please note that now we have to exclude 0 and 2 pi. So we have the integral of these sine functions, and inside the sine function we have t. But please don't forget, we also have the constant 1/2 inside this formula for the cosine functions. Therefore, this also has to be integrated here. Of course, this constant here is not a problem at all for the integration. our actual problem is to find an antiderivative for this function here. Therefore, let's split it up again. Let's write the integral of this function and let's integrate the constant immediately. So we have this integral minus 1/2 x minus pi. And now we realize that this whole part here is actually what we want to have in the end. In other words, this whole function here, which we could call f(n)x, is what should go to 0. And we can show that by using integration by parts. So the question is, what are the correct parts here? And indeed, the only reasonable choice would be to split it up into numerator and denominator. This means first here we have the function u and the other one is our function v prime. And therefore on the side here we have to calculate u prime and v. And now u prime is not a problem because it's simply the chain rule with a function in the denominator. Which means we have sine of 1/2 t squared in the denominator. And in addition, the inner derivative we find in the numerator, which is simply the cosine and the factor 1/2 comes in front. Okay, I would say this was not a problem, and now we have to calculate the antiderivative of this function here. And indeed, this antiderivative is exactly the reason our integration by parts works. More concretely, we see that we get a factor 1/n plus 1/2 in front. And in fact, this is very helpful if we want to calculate the limit n to infinity in the end. But first we should write down the whole antiderivative here, which means we have minus the cosine function. So there we have it, and now we can use the integration by parts formula. And first it just tells us we have u times v. So we have our factor 1/n plus 1/2 and then our fraction of the cosine and sine function. So minus 1 the cosine function divided by 2 times the sine function. And then we just have to put in the two boundary points x and pi. And then integration by parts means we have minus the integral again. However, instead of u times v prime, we now have u prime times v inside. So first we have our nice constant again, and then a whole fraction. And in the numerator, we just have to multiply these two cosine functions. And there the factor minus 1/4 we can put in the denominator. And in fact, in the denominator we don't have so much, we just have our sine function squared. And that's it. And maybe it looks more complicated than before, but please don't forget, now we have this nice factor where n is in the denominator. And maybe in the next step we pull that in front, because then we can just simplify everything behind. And in the left part we can put in x and pi, and then we see if we put in pi here we get out 0, which simply means that only the first part remains here. And in the next one we can just pull out the factor 1/4. Otherwise we can just copy the function and then we have it. Okay, so this is our nice result, and now let's fix our variable x in the closed interval with the given epsilon. So this is exactly as stated in the lemma. For epsilon greater 0 we have x in the interval epsilon to 2 pi minus epsilon. So I would say let's visualize that on the real number line. So there's our interval, and exactly in the middle we find pi. Now we do this simple sketch here because if you look at the function fn, you see that the only problem we can have with it is that the denominator here goes to 0. Therefore let's simply sketch the function sine of 1/2 t, where t is our variable here. So what we get here is simply a stretched sine function where the maximum is at pi. However, of course we are not interested in the maximum, we are interested if this function can get to 0. And now it turns out, as you can see, that if we restrict ourselves to this closed interval, we have a safe distance from 0. So more concretely, the function definitely lies above this line here. And we don't need to know the exact value, we just need to know that we have the safe distance delta. And obviously, this delta depends on the given epsilon. Okay, with that we can look back at our function fn and now I would say let's calculate the supremum norm. This is exactly what we need if we want to show the uniform convergence. More concretely, we want that the supremum norm of Fn goes to 0 if n goes to infinity. And now you already know, the good thing we have here is the constant 1 over n plus 1/2. And now the first estimate we can do here is to consider a triangle inequality by taking the two functions here separately. So maybe let's shortly call them a of x and b of x. Therefore now we have to calculate the supremum norm of a plus the supremum norm of b. And now let's simply estimate these two supremum norms individually. So let's start with a and let's look at the worst case we can have. This means the cosine is 1 and the sine function in the denominator is exactly this delta. This is the largest output we can get. So we have 1 divided by 2 delta. And now exactly the same argumentation works with b. Hence we have 1 over 4 delta squared. However, we also have this integral involved, which means we have to multiply by the length of this interval we have. Or we just estimate the length again, and then we can immediately see it's definitely smaller than pi. Hence, multiplying by pi here is sufficient for the estimate. Okay, so I showed you all the details here, just that you can see that we can send n to infinity and the supremum norm actually goes to 0. We don't have any problems there, simply because our x has a safe distance from 0. So the conclusion is we have the uniform convergence of the function fn to the 0 function. And here as a reminder, please recall fn was given as the sum plus the linear function where pi is involved. And now we have proven the uniform convergence for this to 0, which means we have the uniform convergence of the sum with the sine functions to minus this. And exactly this was stated in the lemma, so we are done with the proof of the lemma. Okay, since this was a technical proof, I would say let's sketch what happens in this convergence. And as always, let's do that by using Python. So here we have the first step, so just the sine function and the linear function. And if we increase it to 2, we already see we could have the convergence in the middle here, but not on the boundary points. And we know this is exactly what happens, because the boundary points here stay at 0. So if we jump to n is equal to 50, we see exactly this behavior here. So let's keep this sketch in mind and let's go to our theorem of this video. So please don't forget, the goal from the beginning was to show the sum with the cosine function. More precisely, we want to show that we have a convergence series here with the value given by this function for every x between 0 and 2 pi. So we see, in this case, the boundary points are included now. In fact, we have uniform convergence here as well, but now on the bigger interval from 0 to 2 pi. This means, in some sense, we have to extend the lemma from before to the boundary points as well. And indeed, this will be one part of the proof that follows now. And there we now can use everything we learned before, especially the lemma with the sine function. And this is really helpful because you see, if we integrate the sine function here, we get the cosine function with the correct k factor in the denominator. Indeed, we want to get from k to k squared, so integration is exactly the right method. Therefore, let's simply use the integration on both sides of the equality. And then the only thing we have to change is the name of the integration variable here. Moreover, you recognize we integrate from x0 to x, and obviously both boundary points should lie in our interval here. So very well, now we can solve the integrals, and we immediately recognize that the right hand side is easy to solve, because it's just an integral of a linear function. Therefore the antiderivative is easy to find. We have minus 1/4 times this function squared. And then we simply put in the boundary points. And there we immediately see we have minus the part here on the right hand side of the theorem. We only have to exchange the order inside the square. Now the part with x0 is not so interesting for us because it simply comes in after integrating. So let's simply call it capital C0. Indeed, in the end we want to show that we get the correct constant as well. But first let's do all the integrations. This was the right hand side, which was not so complicated at all. However, now the left hand side is more complicated because we have to integrate a series. And exactly there, the uniform convergence of this series comes in. Because this is exactly what allows us to exchange the series with the integral. So please always remember, pulling a limit out of the integral is dangerous, but the uniform convergence allows it in this case. So uniform convergence is a strong property and it makes this exchange of limit processes possible. And in fact, what remains here is a really simple integral for us to solve. As mentioned before, the antiderivative is simply given as minus the cosine function. And moreover, the inner derivative brings us to k squared in the denominator. And as before, we just have to put in the boundary points x and x0. And there we have it. Now we see we have minus the left hand side of the theorem. And similarly to before, the part with x0 we can simply put into a constant, c1. And there we have it. This is equal to that, and now we can put it together and remove the minus signs. So we have that the series of the cosine functions with k squared in the denominator is equal to this quadratic function here plus a constant. So let's call this constant simply c. And this is exactly what remains to show. We have to calculate this constant now. And in order to do that, first we should note that after such an integration, this convergence here is still uniform. This is a general fact and easy to show, but we only have it on the interval from epsilon to 2 pi minus epsilon. Hence, at this point, we still don't have the convergence at the boundary points 0 and 2 pi. Since epsilon is arbitrary, we have it for all the other points, but not for the boundary points. But fortunately, we know even more in this case here. In particular, we can use the so-called Weierstrass M-test to get the result that we have the uniform convergence on the whole interval. Indeed, to apply this test we don't need to know much, we don't need to do this calculation from before, we just need to know that the series of 1 over k squared is convergent. In fact, obviously here we have that 1 over k squared is a majorand for this series here. And then the Weierstrass M-test tells us that we have the uniform convergence as well. However, it does not tell us anything about the value, about the limit, so we still need the calculation from before. But the good thing is that now we know that we have a continuous function on the whole interval 0 to 2 pi. Indeed, you should know that the continuity property is conserved under the uniform limit. Moreover, we also know that the right hand side here gives us a continuous function as well. Hence, what we get here are two continuous functions that coincide on the open interval 0 to 2 pi. Indeed, this is exactly what the calculation from above gives us. And now we can just put everything together here and we can conclude that this formula also has to hold on the boundary points. In fact, for a continuous function, there is no choice what happens on the boundary, what happens in the limit, if we already know everything inside. Hence, we get everything we want. We get this equality for all points in the closed interval and also the uniform convergence of the series. And with that, finally, only the calculation of this constant c remains. Hence, this is the last step of our proof here. And here we can use our formula and that we have shown the uniform convergence on the whole interval. So we can just integrate from 0 to 2 pi. And again, as before, the right hand side is really simple. Indeed, we can just write down the antiderivative again and put in the boundary points. And the integration of the constant gives just 2 pi times c. And now we just have one small calculation, namely this one is pi cubed divided by 6. So the only question is, what is about the left hand side? Obviously we just use the uniform convergence again. And then we just have to integrate cosine functions separately. However, this is now an integration over a whole period, which means we have a cosine function which has a symmetry, so we get out 0 for all the integrals. And with that we have it, the constant c can be calculated now. We bring it to the other side, we have a minus sign, we divide 1 pi, and then we have pi squared divided by 12. And that's it. This is the constant we needed, this is the constant from the theorem, and with that we are finished. And with that we have done all the technical calculations we needed, and we can continue our theory for Fourier series with the next video. So I really hope we meet there again, and have a nice day. Bye bye.